So hello guys, today we are starting with our new topic which is ducts. In the previous topic we have seen that design and solving the problem based on the refrigeration system based on the psychrometric chart. Now to transfer the air or cooled air, we require some ducts and transport system that is called duct. So now we have to design the ducts based on the application and its parameters and other things. So in this chapter we will see all these things, starting with chapter introduction. What are the ducts? Ducts are the contents or passage used in heating, ventilation and air conditioning HVAC system to deliver and remove the air. In the right figure we can see the ducts from the big malls and other areas. We see such kind of ducts and industries like ducts are basically used to transfer or deliver the air in centralized air conditioning system to separate rooms and other compartments. The duct system convey the conditioned air from air conditioning equipment to the proper air distribution points or air supply outlets in the room and carry the return air from them the room back to the air conditioning equipment for reconditioning and recirculation. So basically, what are the two to three applications? There are two to three applications of the ducts. Ducts are used to transfer the air to the small rooms and other compartments, as well as it is used to take a return air to the conditioning system or equipment. Now there are moving towards the classification. There are different kind of ducts based on its application. So supply air duct, return air duct, fresh air duct. These first three are the based on the its application for what it's used. So based upon that, its names are taken: supply air duct, return air duct, and fresh air duct. Supply air duct is used to transfer the air or supply the air towards the different rooms or different sections. Return air duct is name shows that it's used to take the return air from the room to central system. And here fresh air duct is used to give the fresh air to the cooling machine or cooling coil. Now depending upon the pressure, again three names are there: low pressure duct, medium pressure duct and high pressure duct. Based upon the different kind of pressures, how it operates, these are the divided into three types. Now depending upon the velocity, ducts are categorized as low velocity duct and high velocity duct based upon its mass flow rate. And other based upon the shape are also there: circular duct, rectangular duct, square duct. These are the types of ducts. Now what kind of pressure are there inside the duct? So there are two pressure inside the duct: static pressure and dynamic pressure. Dynamic pressure is also called as velocity pressure. So we will see one by one. First is static pressure. So static pressure is the measure of the potential energy of the unit of air in the particular cross section of duct. Air pressure on the duct wall is considered as static. Means initially, if there are duct inside the duct, there is some air is present there. So what kind of pressure they exert on the wall of a duct, that is static pressure. The static pressure always exists in duct system since it is not depend upon the air movement. So as we know, static pressure is the pressure when the air is inside the duct, it's at stationary position. So that air exert the pressure on them. That is static pressure. So whether there is force or not force, or either whether pressure applied or not applied, it does not depend upon that. It is it is always there. Static pressure is always there in the duct. So what if the duct is open towards the air? Means fresh air is outside the duct or corner duct system. So in this case, static pressure would be reduced and static pressure would not be considered in that case. So now in the static pressure, It tends to burst a duct when it is greater than the atmospheric pressure and tend to collapse when the force is less than that of atmospheric pressure. So static pressure should be maintained in the range of atmospheric pressure to get a particular application done. So now moving towards the dynamic pressure or velocity pressure. Dynamic pressure is the kinetic energy of a unit of air flow in the airstream. It is equal to the drop in the static pressure necessary to produce a given velocity of flow. Conversely, it is equal to increase of static pressure possible when the velocity is reduced to zero. So what is dynamic pressure? If there is static air present inside the duct, if we provide some velocity to that air, so there it will exert some pressure, extra pressure or low pressure. So that is called velocity pressure or dynamic pressure. The dynamic pressure is a function of both air velocity and density. Dynamic pressure is given by density multiplied by velocity square divided by 2, rho v square by 2. So now total pressure. Total pressure consists of pressure that air exerts in a direction of a flow, its velocity pressure, plus the pressure of air that exerts perpendicular to the container through which the air moves. That is static pressure. In other words, it's algebraic sum of static pressure and dynamic pressure of the velocity pressure. So mathematically it is denoted by Pt. It is total pressure. Total pressure is Ps plus Pv. Ps is static pressure and Pv is a dynamic pressure or velocity pressure. Now statistic and total pressure may be either be positive or negative, but the velocity pressure is always positive. Velocity pressure is always positive, but static pressure is if static pressure is negative, depend upon the atmospheric pressure. So total pressure can be negative or positive, but velocity pressure is always positive. So to get the velocity or area at the other point, we have Bernoulli's equation. So in the diagram, we can see that there are 2 points and different cross section of a pipe. At the point number one, it is A1 P1 and rho 1 B1. A1 is the area of cross section at the point 1, P1 is the pressure at the point 1, rho 1 is the density of air at point 1 and V1 is the velocity at point 1. Similarly, at the second point A2, P2, rho 2 and V2 is denoted. Each direction is rightwards from a higher cross section to lower cross section. So from the Bernoulli's law, for the frictionless, incompressible and steady flow, the Bernoulli's equation is given as P by rho plus V square by 2 plus G into Z is constant. It is Bernoulli's equation. So what are the assumptions? Assumptions are here for the Bernoulli's. The flow should be incompressible, flow should be frictionless, and steady flow should be there. These three conditions should be satisfied by the flow. Then only we can apply the Bernoulli's equation, which is P by rho plus V square by 2 plus Gz, where P by rho is a pressure head, V square by 2 is velocity head, G by Z is static pressure. Now, if we multiply by rho, so we will get P plus rho V square by 2 plus rho GH is constant. Now, applying this equation to two cross section of duct, we will get PS1 plus rho 1 V1 square by 2 plus P1 rho Z1 is equals to PS2 plus rho 2 V2 square by 2 plus rho 2 G Z2. Now, here static pressure, PS1 is a static pressure, PV1 is a V1 is a velocity pressure. In this way, we have equated velocity and Bernoulli's equation to both cross section. Now, since rho 1 and rho 2 is equal and Z1 and Z2 is equal, Z1 and Z2 are equal because there are no such a height difference or no that much cross section area difference or height difference is found there. So ultimately Z1 is equals to Z2. Then therefore the above expression may be written as PS1 plus P1 V1 square rho 1 V1 square by 2 plus PS2 plus rho 2 V2 square by 2. So here PS1 is static pressure and rho V1 square by 2 is dynamic pressure or velocity pressure. We have seen before. Therefore, PS1 plus PV1 is equals to PS2 plus PV2. It is the modified Bernoulli's equation for the pipe or duct system. Now, from the above expression, we find that when the flow is frictionless and there is no pressure drop between the two sections, then the total pressure of two sections would be equal to PS1 plus PV1 is equals to PS2 plus PV2. So total pressure would be equal at both ends. Now, Bernoulli's equation for a duct. In actual practice, there is always a pressure drop in a duct due to friction and other causes such as sudden change in the cross section in the direction. If PL is a total pressure of the drop or pressure loss between two sections, then the previous equation can be written as PS1 plus PV1 is equals to PS2 plus PV2 plus PL. Here PL is a total pressure loss between the cross section. Here, due to some constraint or friction or other things, there is always a pressure drop between two sections. So that pressure drop we should add into our equation to get proper result. Now, in case of fan or blower is introduced between two sections of the duct, then above equation can be other then modified as PS1 plus PV1 plus PTF. So fan power should be added towards the into the equation. So we will final equation we will get as PS1 plus PV1 plus PTF is equals to PS2 plus PV2 plus PL. PL is a pressure loss and PTF is a rise in the pressure due to fan work and it's known as a total fan pressure. So in this way we can equate the equations and then solve the equation. So now point to be noted, the pressure in the ducts are usually expressed in of water. Then the air flowing through the ducts is taken as a standard air unless it is stated. Because if there is given that different cross section or different air property is given, so that we have to take. But if not given, then we have to take as standard air. The standard air is having temperature is 20 degrees Celsius and atmospheric pressure is 1.013 bar. Then for the standard air, the mass density rho A is equals to 1.2 kg per meter cube. And if velocity of air flowing through the ducts is meter per second, then the velocity pressure in a duct is given as. Because if we got the velocity, then we can calculate the pressure velocity PV as rho V square by 2. Here rho A is 1.2 kg per meter cube for a standard air. So 1.2 multiplied by V square by 2 is 0.6 V square Newton per meter square. Now 0.6 V square upon 9.81. If we divide by G, because it is 9.81, so we get the value as V square upon 16.35. So we have divided by G because we have to calculate into of water. We have converted Newton per meter square into of water. We will get V square upon 4.04 multiplied by square of water. So if we are having the velocity of air inside the duct, so we can calculate the velocity pressure or dynamic pressure inside the duct in of water as well as in Newton per meter square. In of water, we can calculate with the help of formula V upon 4.0 square, 0.4 whole square, and in Newton per meter square as 0.6 into velocity square. Now, in the next part, we will see about the numerical. This numerical we will solve in the next class, and that's all for today. We will meet in next video with the solution.